Electrochemistry is the research field that concentrates on studying materials, electrical properties, and chemical reactions. It's the reason batteries store and provide energy, and it's integral to countless processes we encounter daily, from the corrosion of metals to the workings of our own bodies. In this video, we'll explore the fundamentals of electrochemistry and discuss its historical development, basic principles, and various applications. We'll also explore the role it plays in energy systems, material science, and the latest technological advancements. We'll cover everything from the workings of electrochemical cells to the principles of electroanalytical techniques. So strap in as we take a journey through the electrifying world of electrochemistry. Every great story has an origin, and electrochemistry is no exception. Let's travel back in time to the late 18th century when the Italian physician Luigi Galvani made a shocking discovery. While dissecting a frog, he noticed that the legs twitched as if alive when struck by a spark of electricity. Galvani's experiments established a fascinating link between electricity and life, a field now known as bioelectrochemistry. Yet another Italian, Alessandro Volta, wasn't quite convinced by Galvani's theory. Volta proposed that the twitching was due to two different metals causing electricity, not the frog's animal electricity. This argument led him to invent the voltaic pile in the year 1799, the first true battery, which produced a reliable and continuous flow of electricity. Fast forward to the 1900s and we meet Michael Faraday, an English scientist who contributed immensely to the field. Faraday's experiments on electrolysis not only established the laws that govern the process but also introduced terms like anode, cathode, ion, electrode, and electrolyte, words we use today without a second thought. But the story of electrochemistry isn't just about these three men. It's about countless other scientists who built upon these early discoveries, pushing the boundaries of knowledge and unlocking new technologies and applications. From the lead-acid battery in your car to the lithium-ion battery in your smartphone, from corrosion prevention to electroplating and even the electrochemical sensors monitoring glucose levels in diabetics, all these can be traced back to the foundations laid by these pioneers. So as we delve deeper into the world of electrochemistry, let's remember this journey of discovery, of curiosity, and of human ingenuity. These pioneers laid the foundation for the electrochemical wonders we witness today. Just like building a house, understanding electrochemistry requires a strong foundation. Diving into the basics, let's start with oxidation-reduction or redox reactions. These involve the transfer of electrons from one atom, ion, or molecule to another. The entity that loses electrons is said to be oxidized, while the one gaining electrons is reduced. Remember, it's not about losing or gaining weight, but electrons. Moving forward, let's talk about electron transfer processes. These are central to electrochemistry. Whenever a redox reaction occurs, electrons are transferred from the reducing agent to the oxidizing agent. This transfer can happen directly or through a conductive connection, like a wire or an electrode. Imagine it like a game of hot potato, but instead of a potato, we're passing around electrons. Now, what would our electrochemical world be without electrolytes? These are substances that, when dissolved in water, break down into ions and are able to conduct an electric current. It's like they're the conductors of a grand orchestra guiding the flow of electricity. They play a crucial role in electrochemical cells, helping to complete the circuit and making the magic of electrochemistry possible. So we've got redox reactions where electrons are passed around. We've got electron transfer processes, the mechanism of this pass-the-parcel game. And we've got electrolytes, the essential conductors that help to orchestrate this whole process. These are the fundamental principles that underpin electrochemistry. Understanding these principles is like learning the alphabet before you start to read or write. Once you've got a handle on these basics, you're ready to delve deeper into the world of electrochemistry, to explore its many applications, from batteries and fuel cells to corrosion science and electroplating. With these principles, we can start to unravel the complexity of electrochemical processes. Electrochemical cells, they're not just components of a high school science project. At their core, these cells facilitate redox reactions, the crux of many processes that power our everyday lives. The two primary types of electrochemical cells are galvanic cells, also known as voltaic cells, and electrolytic cells. Galvanic cells convert chemical energy into electrical energy. They consist of two half cells, each containing an electrode immersed in an electrolyte. One of these half cells undergoes oxidation, losing electrons, while the other undergoes reduction, gaining those electrons. The movement of these electrons from the anode, the electrode where oxidation occurs, to the cathode where reduction occurs, generates an electric current. The quintessential example of a galvanic cell is a battery, powering everything from flashlights to electric cars. On the other hand, electrolytic cells do the opposite. They use electrical energy to drive non-spontaneous chemical reactions. An external power source supplies the electrons that facilitate these reactions at the electrodes. The electrolysis of water, where water is broken down into hydrogen and oxygen gases, is a classic example of an electrolytic cell in action. Both types of cells play a pivotal role in various fields. Galvanic cells, in the form of batteries, power our devices and vehicles, making modern life possible. Electrolytic cells enable us to produce a range of substances, from chlorine gas for water treatment to precious metals for jewelry. A key point to remember is that these cells function based on the same fundamental principles of redox reactions and electron transfer. The difference lies in the direction of electron flow and whether the process is spontaneous or driven by an external source. So, next time you switch on a light or drive a car, remember the humble electrochemical cells working behind the scenes, translating chemical reactions into practical applications that shape our world. From batteries to electrolysis, these cells power our world. Thermodynamics isn't just about heat and work, it's also crucial in understanding electrochemical systems. And at the heart of this understanding is a concept called Gibbs free energy. Gibbs free energy, named after the American scientist Josiah Willard Gibbs, is a thermodynamic potential that measures the maximum reversible work that a system can perform at a constant temperature and pressure. It's a valuable tool in predicting the feasibility of a reaction. In an electrochemical cell, the change in Gibbs free energy is equal to the negative product of the number of electrons transferred, the Faraday constant, and the cell potential. This relationship is the foundation of the Nernst equation, a crucial tool in electrochemistry. The Nernst equation provides a way to calculate cell potentials under non-standard conditions, factoring in the concentrations of reactants and products. Imagine a reaction where the reactants are being converted to products. As this reaction progresses, the concentration of reactants decreases and the concentration of products increases. The Nernst equation allows us to calculate how the cell potential changes as this reaction progresses, but how do we know which direction a reaction will proceed in the first place? That's where the electrochemical series comes in. The electrochemical series is a list of elements arranged according to their standard electrode potentials. Elements with higher electrode potentials tend to gain electrons or be reduced, while those with lower electrode potentials tend to lose electrons or be oxidized. This series is significant because it allows us to predict the direction of redox reactions. If we place two elements in contact, the one higher in the series will tend to be reduced and the one lower will tend to be oxidized. So, thermodynamics, through the concepts of Gibbs free energy and the electrochemical series, provides the framework to understand the behavior of electrochemical systems. It's the dance between energy and matter that drives these systems, and understanding this dance is key to harnessing the power of electrochemistry. The dance between energy and matter is what drives these electrochemical systems. Electrochemistry plays an instrumental role in our ability to analyze and understand the world around us. This branch of science has fostered the development of numerous analytical techniques, each with its unique principles and applications. Let's dive into some of these electroanalytical techniques. First up, we have potentiometry, a method that measures the potential difference between two electrodes. This technique is the cornerstone of pH meters and ion-selective electrodes, tools that have become indispensable in laboratories worldwide. Next, we have coulometry, a technique that quantifies the amount of matter transformed during an electrochemical reaction by measuring the total charge passed. Think of it as a chemical scale, providing precise measurements of substances involved in a reaction. Then we have voltammetry, a method that sweeps the potential of an electrode and measures the resulting current. It's like an investigative tool, providing insights into oxidation-reduction reactions and the electroactive species present in a system. But the wonders of analytical electrochemistry don't stop here. The field has given rise to the development of electrochemical sensors and biosensors, devices that transform chemical information into an electrical signal. These tools are the unsung heroes of our everyday lives. Take glucose monitoring, for instance. Diabetic patients rely on electrochemical biosensors to routinely check their blood glucose levels. These devices measure the current produced by the glucose oxidase reaction and correlate it with the glucose concentration in the blood. Then we have environmental sensing. Electrochemical sensors are employed to monitor pollutants in air and water. They can detect harmful substances like lead and mercury, providing crucial data for environmental protection efforts. From diagnosing diseases to monitoring environmental pollutants, electrochemistry is our silent detective. It helps us to uncover truths that lie beneath the surface, deciphering the language of molecules and ions. As we continue to innovate and refine these techniques, we strengthen our ability to navigate and understand the complex chemical landscape of our world. Electrochemistry isn't just about understanding the world, it's also about powering it. At the core of this power, we find batteries and fuel cells. Let's start with batteries, which we encounter in our everyday lives. Batteries operate on the principle of redox reactions, converting chemical energy into electrical energy. They come in various forms, from the small alkaline batteries in your TV remote to the massive lithium-ion batteries that power electric vehicles. Each type of battery boasts a unique energy density and efficiency, making them suitable for different applications. Fuel cells, on the other hand, are a bit different. They convert chemical energy directly into electrical energy, but unlike batteries, they don't run down or need recharging. As long as there's a supply of fuel, they'll continue to produce energy. Fuel cells are used in a variety of applications, from powering spacecraft to providing electricity in remote locations. But electrochemistry doesn't stop at powering devices. It also plays a critical role in producing chemicals and materials through a process known as electrolysis. This process involves using an electric current to drive a non-spontaneous chemical reaction. One common application of electrolysis is the production of hydrogen, a clean-burning fuel that holds promise for a sustainable energy future. Another fascinating application is organic electrosynthesis, where electricity is used to catalyze the formation of complex organic compounds. These are just a few examples of how electrochemical energy systems are shaping our world. From the batteries that power our devices to the fuel cells that might one day replace traditional combustion engines, electrochemistry is playing a crucial role in our energy systems. And with the growing focus on sustainability and clean energy, the importance of electrochemistry is only set to increase. Electrochemistry is at the heart of our energy systems, fueling our progress. Corrosion might seem like just a nuisance, but it's a major concern that electrochemistry helps address. On the surface, corrosion is simply the gradual destruction of materials, especially metals, by chemical reactions with their environment. But when we zoom in, it's a complex process involving electrochemical reactions. At the heart of corrosion is a two-part process, oxidation and reduction, collectively referred to as a redox reaction. Oxidation is the loss of electrons and reduction is the gain of electrons. In the context of corrosion, a metal surface, say iron, loses electrons and oxidizes to form iron oxide, commonly known as rust. The rate of corrosion can be influenced by numerous factors, including the nature of the metal, the presence of certain ions in the environment, temperature, and the acidity or alkalinity of the surrounding medium. This is where electrochemistry steps in to provide strategies for controlling and preventing corrosion. One of the most common strategies is cathodic protection. This process reduces the oxidation of the metal by making it a cathode in an electrochemical cell. This can be achieved by attaching a more easily oxidized metal to the material we want to protect. The sacrificial metal oxidizes instead, sparing the original material from corrosion. Another strategy is the application of coatings and paints that act as physical barriers, preventing the environment from coming into contact with the metal surface. Now, let's pivot to a more constructive aspect of electrochemistry, electroplating and surface treatment processes. Electroplating is the process of depositing a layer of metal onto a surface to provide a decorative finish, add wear resistance, reduce friction, or achieve other desired properties. In an electroplating setup, the object to be plated is made the cathode in an electrolytic cell containing a solution of metal ions. When electric current is applied, metal ions in the solution are reduced and get deposited on the object. From preserving our infrastructure to creating stunning jewelry, electrochemistry ensures our world remains vibrant and strong. We've journeyed through the electrifying world of electrochemistry, but there's still so much more to explore. From the historical milestones of electrochemistry, we've seen how the pioneering work of luminaries like Luigi Galvani, Alessandro Volta, and Michael Faraday laid the foundation for this fascinating field. We've delved into the fundamentals, understanding the principles of redox reactions, electron transfer processes, and the role of electrolytes in conducting electric current. We've differentiated between galvanic and electrolytic cells and grasped the thermodynamics of electrochemical systems, including the relationship between Gibbs, free energy change, and the electromotive force of a cell. We've seen how the electrochemical series predicts the direction of redox reactions and cell potential, and how electron transfer kinetics, including overpotential and the Butler-Volmer equation, influence electrochemical reactions. We've also explored the realm of analytical electrochemistry, understanding techniques like potentiometry, coulometry, and voltammetry, and how they aid in analysis. We've delved into the principles of electrochemical sensors and biosensors and their myriad applications, from glucose monitoring to environmental sensing. In the field of energy systems, we've learned about the principles, types, and applications of batteries and fuel cells, and the role of electrochemistry in producing chemicals and materials, such as hydrogen and organic compounds. We've understood the electrochemical mechanisms of corrosion and strategies for its prevention, as well as the principles and applications of electroplating and surface treatments. As we've seen, the field of electrochemistry is not static, it's evolving and expanding, with advancements in nano-electrochemistry, green electrochemistry, quantum electrochemistry, and solid-state electrochemistry. These developments promise exciting future prospects, from new energy storage solutions to sustainable technologies and novel materials. The road ahead is bright as we continue to innovate and discover. Electrochemistry, with its blend of chemistry, physics, and engineering, truly has the potential to light our path forward, solving some of our most pressing challenges, from energy storage to environmental sustainability. As we continue to journey through this electrifying world, let's keep sparking curiosity. Until next time, keep sparking curiosity.